Okay, so besides the fact that transition metals have exceptions with regard to how we go from an atom to ion, they fill in the same way as every other element on the periodic table when you using the same rules when you're just doing the atom. But again, when we ionize, we see some differences. And even within transition metals, we have a couple of transition metals that are going to have even um, another exception, and those are going to be copper and silver, as well as chromium and molybdenum. And these there's a reason why they're in the same columns and they're spaced similar apart, and we'll get to that in a sec. What we're going to do is the question is specifically asked. So I made a statement that most transition metals have a +2 ion, but there are some that are more likely to be +1, and the question is why. So we're going to do copper, and everything applies for silver. So we're going to look at copper first. So if we look at the periodic table, copper has atomic number of 29. So that's 29 electrons. Okay. So we're going to do the energy level diagram for copper. So we have 1s, 2s, 2p, 3s, 3p, 3d, and then we have 4s. And we fill in electrons. We'll do in blue. So we have 29, but remember that we can go all the way up to 3p, and we know that's 18. So I'm going to do that. That's argon. That's 18. And then I'm going to go 19, 20. And now I have 9 more to go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you'll notice, so this is what we call a D9 configuration. D9 configuration is very close to a D10 configuration. We call this a noble gas electron configuration. Now this is very stable. And so copper is very, very close to being this configuration. And so what copper does, its ground state, this is an exception to its ground state, not to an ionization, is that we're going to take, because we're so close to a D10, we're going to take this electron and we're going to move it from the higher energy 4s, because once we have that there, it's going to be higher energy, and move it down there. So then this electron goes away, and we're going to put it, I'll do it in red, so we know where it came from, right there. So what happens is the ground state configuration of copper is actually, so we would assume, well, let me write what it actually is first so we don't get confused, is argon. Again, that's argon is everything up to here. And then we have 3D10 for S1. We would normally assume that copper, this is what you would put based on the rules we have, 3D9 for S2. So that is not correct. And so it's actually what we have here. So you have to start off from that point. And if we, to answer the question, this makes a lot of sense, because why is copper always +1? Well, what electron are we going to remove first? Well, we're going to remove, so the 4s electron, again, there's only one, is removed first. So that gives us the copper +1. But why don't we make copper +2? Well, to make copper +2, so copper 2+ would go from a D9 conformation, or sorry, from a D10 conformation, D10, yay, to a D9 conformation. Oh. And so it's destabilizing. Where D10 is a noble gas configuration. We have a full octet. We filled up all our d orbital. Well, it's not an octet, but we filled our d orbital. And so the general rule here is that a fully filled d orbital is lower energy or more stable, however you want to think about it. Stable than an almost. So fully filled orbital, that's going to be D10. Then a almost fully filled d orbital, and that would be a D9. And so because of that, we're going to see this trend. Now for chromium and molybdenum, we will see a very similar trend. Now both of these are, if we just draw out the last part of this diagram, 4s has 2, and then the D has, so 3D has 1, 2, 3, 5. Now chromium, molybdenum, so this would be for chromium because it's we're talking about 3s, is going to be 3D4. So D4, kind of like D9, but now instead of being fully filled, we're almost half filled. And so we're going to do the same thing here, where this electron is going to get moved down. And so the conformation for chromium is going to be argon 3d5 for S1. For molybdenum, we just increase everything. We go to krypton, that's down 1, and then 4d5, 5s1. So it's a d5 s1 conformation for the ground state, and we see that for silver. If we write that here, silver would be Ag. It's ground state. It would be krypton, down 1, and then we just increase each number, so it's 4d10, 5s1. Okay, so those are the ground states for copper and silver, chromium and molybdenum. Those are your 4 exceptions to the ground state conformation for transition metals. Just know those. Those will pop up for sure on exams, both my exams and the American Chemical Society exam. So just be aware. And I guess to point out here is, so we said a fully filled d orbital is lower energy, so a fully filled. So a half filled. So we have the same kind of thing here, that a half filled d orbital is more stable than a almost half filled d orbital. And so we'll see the same trend there. So that's the exception. Make sure you're aware of it. And so to answer the question, we drew those energy level diagrams, we ionized, and we see that to go, the full answer to this question would be showing that to go to a 2+ ionization for copper or silver, you'd go from a D10 conformation to D9, and that would be destabilizing. That would be a complete answer.